Hello, I am Václav Novotný and welcome to the tutorial of energy sources and conversions. This tutorial will be focused on a fuel cell. So, what is actually the fuel cell and how does it work? So, in standard power plants, the method of energy conversion is that we have some chemical energy in the fuel and we burn it to get thermal energy. Then from thermal energy, the thermodynamic cycle makes mechanical energy, and generator converts rotational kinetic energy to electrical one. In the fuel cell, the method of conversion is much more straightforward. It's directly chemical to electrical. Therefore, we also call it direct conversion. The principle can be seen on the figure over here. We have the fuel. For simplicity, here the most basic fuel cell using hydrogen and oxygen. So hydrogen comes towards one porous electrode. There it dissociates to provide electrons and protons. The proton is transferred through the proton exchange membrane to the cathode, to other electrode, where it recombines with dissociated oxygen, and hydrogen plus oxygen makes water. The oxygen as oxidizer comes from down here, also towards this porous electrode. In order to have the recombination on this electrode, the electrons need to transfer through the electrical circuit, and that's the electricity that was produced. So these systems can work with various fuels, but only in gaseous or liquid form, as hydrogen, methane, or for example methanol. The oxidizer is oxygen, either pure oxygen or air can be used where just oxygen from the air is the component that reacts. And the electrically charged ions go through the electrolyte. It can be acid, it can be some base, or it can be, as was the case in here, membrane, for example here, because the proton is the transferring ion, so it's proton exchange membrane, PEM. The limitation of the fuel cell is in the current density, typically given in amperes, or more likely milliamperes per square meter. So the power is based on the area. For example, if the power density is half watt per square meter, so 100 kilowatt system would require 20 square meters of the surface of the electrode, of the electrodes and of the membrane. The fuel cells can be classified based on their operating temperatures. We have low temperature systems, typically the hydrogen membranes with the hydrogen fuel cells with the Nafion proton exchange membrane, operating between 60 to 130 degrees C. Then we have mid-temperature systems, 160 to, let's say, 220, and then high temperature, for example, solid oxide fuel cells operating over 600 degrees C, basically up to material limits. So now we will have a look at the fuel cell example, which we will calculate. So we will assume the hydrogen fuel cell with the Nafion membrane, where on the cathode takes place fuel oxidation, meaning electron release, which is the hydrogen, or actually here in the reaction 2 hydrogens dissociate to 4 protons and 4 electrons. Then the protons transfer through the membrane, electrons go through the circuit, and on the anode takes place oxygen reduction. So first the oxygen also needs to dissociate. So from 2 oxygen molecules, when we add 4 electrons, we will get 2 molecules of oxygen 2-, and then these oxygen 2- combine with the protons transferred through the membrane, and we will get 2 molecules of the water that goes out. And the task is to determine the maximum conversion efficiency of chemical energy in the fuel to electricity of this fuel cell when we are using pure hydrogen as the fuel and oxygen as oxidizer. The conditions of the reaction are that it takes place at 100 degrees C and standard atmospheric pressure. And just we have here a note: if we would combust the hydrogen at this low temperature, so the Carnot efficiency of cycle that we could get on it would be with maximum temperature 100 degrees C, rejection temperature 25 degrees C, so the Carnot efficiency would be 20.1%. We will compare the fuel cell to this value. So, our calculations will be referenced to the chemical reaction where one molecule of hydrogen is combined with half molecule of the oxygen, and from that we will get one molecule of water. And in order to get the energy from this reaction, so the energy that we will get is some heat and some work, and the heat and work together are given by something called difference in enthalpy of formation. And this difference in enthalpy of formation is the enthalpy of formation of products, enthalpy of formation of H2O, minus enthalpy of formation of reactants, which is enthalpy of formation of the hydrogen, plus half of the enthalpy of formation of oxygen molecule. And because we will calculate everything with respect to moles, so we will use bar to denote that these are parameters with respect to single mole. So now how to get the enthalpy of formation. There is something called standard enthalpy of formation at reference temperature of 25 degrees C and the reference pressure of standard pressure 101.325 kilopascals, and it's denoted as enthalpy of formation 0. And then we will need to add the enthalpy difference given by the different temperature that we have. So here we have the temperature 100 degrees C. So we need to get the difference between the enthalpy at 100 degrees C and enthalpy at 25 degrees C. So for that, if we have some formulation of enthalpy, we can get the enthalpy for the given temperature minus enthalpy at the reference state, in this case the 25 degrees C. So let's start with the water, where for the enthalpy of formation at standard conditions, we can have a look at, for example, some chemical tables, something that we have in here: enthalpy of formation, Gibbs function of formation, and absolute entropy at 25 degrees C and 1 atmosphere. And here we will find the water, and we have actually two waters, water and water vapor. And because the product of this reaction is the water is not dripping from that, or we cannot anyway use the condensation heat, so we will use the parameters for the water vapor. So we can see the value of the enthalpy of formation being minus 241,820 kilojoules per kilomole, or minus 241.82 kilojoules per mole. Now we will get the enthalpy at the 100 degrees C, and because our reaction takes place in gaseous form, so in the property functions, because it doesn't change much with the pressure, so just make sure you use sufficiently low pressure to have the gaseous form. So it will be function of temperature, and for pressure use, for example, 2 kilopascals. And from some steam property functions or steam tables, you would get the value of 2688.44 kilojoules per kilogram. Now the molar weight of water is 18.015 kilograms per kilomole. So we can get the molar enthalpy at 100 degrees C, being the enthalpy at 100 degrees C which we just got, multiplied by the molar weight, and we will get number 48,432.9 kilojoules per kilomole. Now we can do the same for 25 degrees C, the standard conditions. So again, function of temperature and pressure. Here especially is important the low pressure, so that we stay in the gaseous form. And we will get enthalpy 2547.09 kilojoules per kilogram, and the molar enthalpy at the standard temperature would be the enthalpy that we just got, multiplied again by the molar weight, and we will get value of 45,886.5 kilojoules per kilomole. So with this, we can get the enthalpy of formation at the given temperature, for the water vapor, which is this enthalpy at the temperature of standard conditions plus the difference between these two, and we will get minus 273.6 kilojoules per kilomole. That's the first enthalpy of formation that we got for the products for the water. Now we do the same with the reactants. So for the hydrogen, the enthalpy of formation at standard condition is, as you can see over here, 0, because it's a reference condition, so it's nice that we don't need to calculate anything more from that. Kilojoules per kilomole. The molar weight of the hydrogen molecule is 2.016 kilogram per kilomole. The enthalpy at 100 degrees C is again enthalpy as a function of temperature and pressure, where now you can use also the pressure 1 bar because it's still well within gaseous form, and we would get 5011.86 kilojoules per kilogram, 0.68 kilojoules per kilogram, and from that we will get enthalpy of the molar enthalpy at 100 degrees C as 10,102.95 kilojoules per kilomole. Now the same for 25 degrees C. So the enthalpy is 3931.80 kilojoules per kilogram, which translates into molar enthalpy of 7926.04 kilojoules per kilomole. So the enthalpy of formation for the hydrogen at 100 degrees C will be the enthalpy reference over here, 0, plus the change in the enthalpy for the new formulation between the given temperature and the reference temperature. So when we put it together, the result is 2176.9 kilojoules per kilomole. And finally the oxygen. So again the standard enthalpy of formation is 0. Now from property functions, enthalpy at 100 degrees C would be 340.5 kilojoules per kilogram. And with the molar weight of 31.998, so basically 32, kilogram per kilomole, we will get the molar enthalpy 10,895. 0.29 kilojoules per kilomole. Doing the same for the standard conditions. The enthalpy is 271.0 kilojoules per kilogram, which translates into 8,672.10 kilojoules per kilomole. And the enthalpy of formation will therefore be, for the oxygen, 2223.20 kilojoules per kilomole. So now we have all the enthalpies of formation, and we can get the difference in the enthalpies of formation. So water minus the hydrogen minus half of the enthalpy of formation of oxygen. So it would be minus 242,562 kilojoule per kilomole. Now, similarly as in the thermodynamics of the thermodynamic cycles, where we had the reversible component of the heat that was possible to be converted to work and electricity, and then the irreversible part of the heat, and as the change in the entropy or the increase of the entropy did not allow us to convert all the heat into the electricity, so we have something similar over here. So this change in the enthalpy of formation can be also written that it has two components, and it's the change in the Gibbs free energy, which is the maximum possible work or electricity that can be obtained out of the chemical reaction, plus the irreversibility of this reaction, which is absolute temperature times change in the entropy, so T delta S. And obviously it's the Gibbs free energy that we want to get to see what's the maximum theoretical work or maximum theoretical electricity that can be obtained from the content of the fuel, which is the change of the enthalpy of formation. So we can already see that the efficiency of the fuel cell, of the theoretical one, would be the change in the Gibbs free energy divided by the change in the enthalpy of formation. We have the temperature, it's the 100 degrees C or 373.15 kelvins, but we need to get the change in the entropy. So let's go for the entropy calculation. So in the property tables, if we start with the water vapor, so we can see the entropy at the standard conditions, which is 188.83 kilojoules per kilomole and Kelvin. And you can already guess that the principle of calculation will be nearly the same as for the enthalpies. So here we will have entropies. And so the entropy S0 was 188.83. kilojoules per kilomole and Kelvin. Entropy at 100 degrees C based on temperature and pressure is approximately 9.2 kilojoules per kilogram, which then translates into entropy for the molar conditions and 100 degrees C, which is 165.628 kilojoules per kilomole. Same for the 25 degrees C. Entropy 8.771 and molar entropy is then 158.01 kilojoules per kilomole. So we can get the molar entropy of water at 100 degrees C as the standard molar entropy, again plus the entropy change and we will get value of 196.44 kilojoules per kilomole. So that was the water. Same goes for the hydrogen. So you can see the entropy at the standard conditions. The absolute entropy for hydrogen, 130.68 kilojoules per kilomole and Kelvin. And now the entropy at 100 degrees C is 56.66 kilojoules per kilogram and Kelvin. Which is 114.22 kilojoules per kilomole. For 25 degrees C, it's 53.43, which translates into 107.71 kilojoules per kilomole. And we get the molar entropy at 100 degrees C for the hydrogen, which is 137.19 kilojoules per kilomole. And lastly, the oxygen. Absolute entropy 205.04. The entropy at 100 degrees C, 6.618 kilojoules per kilogram Kelvin, which translates into, with the molar weight, translates into 211.78 kilojoules per kilomole. And for the 25 degrees C, the entropy from property functions is 6.411 kilojoules per kilogram and Kelvin, which translates into 205.13 kilojoules per kilomole. And putting that together, we get the entropy at 100 degrees C, the molar entropy for oxygen. So it's 211.690 kilojoules per kilomole. So here you can see that the value is almost the same as it was here in the 100 degrees C, because the reference is probably for the entropy very similar, as the standard molar entropy, the absolute molar entropy here was 205 from the chemical tables, and from our property functions we get for the 25 degrees C almost the same value. So here in this function, for enthalpy, or respectively also similarly entropy, where we have given the reference from the chemical tables and then conversion to arbitrary property functions, since we have the reference almost same as here, so basically this is this value could be taken directly. However, it's not the case for most of the property formulation, so that's why we are doing it this way. But now when we have the temperature and the entropy, so we can get the Gibbs free energy as the change in the enthalpy of formation minus the temperature, 373.15, times the delta S, and this delta S will be, similarly as we had for the enthalpy of formation, will be entropy of the products, so entropy 100 degrees C H2O minus entropy of sum of entropy of reactants, which is molar entropy at 100 degrees C of the hydrogen plus 1/2, because we have half of the molecule, entropy at 100 degrees C of oxygen. So this entropy change would be 196 minus 137 and half of 211, which is 105, and we will get value minus 45.74 kilojoule per kilomole and Kelvin. So the TDS itself would be minus 17,069 kilojoule per kilomole. And now we have the enthalpy of formation, the change of the enthalpy of formation, negative value over here, negative because we are producing energy out of the system, minus TDS. TDS is negative value, so we will produce less of the energy as convertible to work. And the change in the Gibbs free energy is thus minus 225,492, in our case 0.7 kilojoule per kilomole. And with this, the change in the enthalpy of formation and the change in the Gibbs free energy, we can get the theoretical maximum efficiency of the fuel cell, and it would be 92.96%. So this is the maximum efficiency that we could get from completely reversible system. But before we have a look at the further details, let's have a look at these maximum theoretical limits. Here we are having a chart of maximum theoretical efficiency of systems for converting fuel or heat into work or into electricity. And we can see in the pink or purple that the Carnot cycle with the low temperature, the temperature of heat rejection being 25 degrees C, has the characteristics of steady increasing efficiency. It can never reach 100% because we cannot reject the temperature, we cannot reject the heat at 0 kelvins, but only at 25 degrees C. If we have a look at various conversions of fuels directly into work, so here we have three cases. The black one is the hydrogen and oxygen to the water, and you can see that the curve starts in about 95%, and actually as the temperature is increasing, so the reversible work obtainable from this chemical reaction is decreasing. At 100 degrees C, we had the calculated case of 93% approximately, and then it continues going down. If we would have a reaction of methane with oxygen, so here we can see that the chemical balance works in the way that the curve is nearly constant. The decrease or increase in the efficiency is nearly negligible, but stays practically at constant value. And also the theoretical limit is a little bit higher. For the reaction of the CO, carbon monoxide plus oxygen, this reaction produces more entropy, so we can see that the curve starts lower and the slope is just slightly higher in the decrease of the efficiency with temperature than the hydrogen fuel cell. Now, from the Gibbs free energy, we can also calculate the theoretical voltage on the electrodes. And theoretical means reversible. So for this, it's obtained as change in the Gibbs free energy divided by the number of electrons that participate in the reaction So since in our reaction from the dissociated form it would be 2 protons plus oxygen 2 minus goes to water, H2O. So we can see that those are 2 electrons. So the N would be 2. And then Farad constant, which is 9.6481 coulombs per mole, and times 10 to the 4. So if it's per kilomole, so it ends up to be 9.6481 times 10 to the 7 coulombs per kilomole. So from this we would get the reversible or theoretical voltage on the electrodes. You would get value minus 1.16, but the minus just defines the polarity of the electrodes. So we can write the change in the Gibbs free energy is an absolute value. Perhaps we can write it like this. So it's 1.685 volts. Now the real voltage of fuel cells is the experimental determined for each case, based on how well you manufacture it, what catalysts do you use on the electrodes, etc. And the typical values are between, let's say, 0.5 to 0.9 volts. So we will assume that the value will be, in our case, 0.8 volts. And then we will have, or basically all fuel cells have some coefficient of fuel utilization, which we will denote as UF. And in our case it will be 0.95. So there is 5% of the fuel that would not get utilized but would cross over the membrane or through some leakages to the side of the products and exit with that to the outlet. So now when we have the real voltage, so we can calculate something called voltage efficiency, which is the actual voltage divided by the theoretical voltage so real voltage divided by the reversible voltage, and for our values it is 0.68. So 68.46%. And finally we can calculate the efficiency of the whole fuel cell, which is the efficiency of the reversible thermodynamic conversion multiplied by the voltage efficiency and multiplied by the fuel conversion factor. So the reversible efficiency was about 93% for 100 degrees C, the voltage efficiency 68%, and the fuel conversion factor 95%, which yields the fuel cell efficiency of 60.46%. 46%. Now similar efficiency would be also the efficiency of electrolysis when producing hydrogen. So if we would assume the whole conversion of electricity to hydrogen and back to electricity, so the values can be in a range of about 30 to 40%. Which is definitely not very much, but the hydrogen is fuel that can be somewhat stored. And as the last thing, let's have a look at the voltage current density chart and see where are the losses in this system. So first we have voltage of the reversible ideal reaction, the reversible theoretical cell voltage over here, delta E ref, but in open circuit real fuel cell, you have some overpotential that decreases the voltage to the open circuit voltage that you actually measure. So it's a first major loss. Then, once you start drawing some current out of the fuel cell, so there are other losses. Very quickly, the voltage would drop down because of activation polarization. Then, as you increase the current density, so the fuel conversion factor might decrease because there is higher possibility of the fuel to cross over to the products, and also due to the higher current there will be higher ohmic losses. Typically the operation of the fuel cell is some trade-off between the current density, so that the fuel cell has given size, and the cell voltage not to be too low, so let's say it would be somewhere here. Then as we increase with the current which is drawn out of the fuel cell, so we get into the point where the polarization loss will further increase as so-called concentration polarization loss, which is caused by the limited mass transfer on the electrodes. So this was the tutorial on the fuel cell, how it works and how to calculate its parameters.